Okay? All of this stuff that we're doing with limits, and if a limit exists, and if a function value exists, okay? Why have I been drilling you on all of this stuff, okay? We have what we call we have continuity, okay? A curve is continuous if there is not a hole or a break in the graph. Plain and simple. A hole makes it discontinuous. If you can draw a piece of your graph, or if you can draw your graph without lifting your pencil, it is continuous everywhere. Okay. Algebraically, let's talk about how we can recognize if we have continuous versus not continuous. Okay? A polynomial will always be continuous. Always. Okay? Polynomials are nice, smooth curves, no holes, no breaks. Nice and continuous. Okay? Rational functions are continuous except where the denominator is 0. What could happen if our denominator is 0? We either have a hole or an asymptote, okay? Which we could consider a break in the graph, okay? A hole makes it discontinuous. An asymptote breaks up the graph and makes it discontinuous, okay? Now, in between, we would say that it's continuous, like in between a hole and an asymptote, but the graph as a whole would not be continuous. Okay. Continuity. This definition is important. There are 3 things that have to happen in order for a function to be continuous. You need to know these 3 things, and you need to be able to, like, this is a way that we prove whether something is continuous or not. You cannot forget these 3 things. Okay, number 1. Okay, so this is continuity at a point. Okay, is it continuous at x equals 1? How do I figure that out? Okay, so number 1, f of c is defined. What does that mean?
It means that all points are actual points.
Okay, we have a point. All right, exactly. Okay, so we're just talking about continuity at one point here. So at x equals c, we have a point. Number 2, the limit as x approaches c of f of x exists. So we have a limit that exists at c. And then whatever your limit is that exists needs to equal the function value. We need a point, we need a limit, the limit and the coordinate need to be one and the same. Okay, that's what those 3 things say. You will be asked to repeat these 3 things.
When you say we need a limit of the point, we need to use the
This notation would probably be good. Okay, so what does it look like? Okay, first of all, I want to go through some counter examples. What do I mean by counter examples? Okay, so it's breaking the rule. So f of c is defined. Nathan said that there should be a point there. So if there's not a point there, f of c is not defined. Okay, if there's a hole, there's no point, if there's no value, if there's no coordinate at c, f of c is not defined. Okay, next one, the limit doesn't exist. Okay, well here I have a function value, but the limit doesn't exist. Well done.
It doesn't exist.
Right. What? Well, the limit needs to exist like as x approaches c. Okay, so not from just the right to left, all right?
So, they can ask him
I should have learned about mapping between you.
We're talking about being continuous at one point. So we're talking just right now about point C.
It just seems like continuity seems like it applies more to like a whole lot.
Well, okay, to say that we're continuous from A to B, right?
You need all points, you need points.
Exactly. Okay, does that make sense? If we're going to talk about like an interval of continuity, all the points in that interval have to meet these specifications.
Okay, so if you just drop the word continuity, you mean a certain point, not an interval. So you state interval if you want to. Does that make sense?
Right. So right now we're talking about points that are breaking our rules for continuity. Right? Okay.
If you
So
had like a break on the outside of the red lines, it wouldn't matter if you were trying
it depends. It depends. Like if we're talking about like the entire graph or a piece of the graph, because we can talk about continuity in its entirety or like this piece of the graph, and we're gonna get to that. So hold on. Okay. So now in this picture, I have a function value. I have a limit that exists, but they're not the same. They have to be the same so that coordinate can fill in that hole. Okay. So this is not continuous. We have a value and we have a limit, but it's not continuous. Okay. So let's look at some graphs. Okay. This graph right here, this is continuous everywhere. Y equals the sine of x is always continuous, right? Okay. Now, what about our greatest integer function? Okay, it is not a continuous function, but we could talk about continuity on an interval, right?
From 0,
Okay, from 0 to 1 we have continuity,
except that 1.
and 0.
and 0, right? So we have continuity from 0 to 1. We have continuity from 1 to 2, but we just don't have continuity from 0 to 2, right?
Yeah.
So technically, if you do have, like if you do x equals 1, there is a point, it's just
Not obviously.
Yeah, but the limit and the point is 0.
Okay, so we could say that it, how do I want to say this? Very carefully. Thank you. Okay. We can say, okay, so let's look at like this graph down here, right? This semicircle, okay? We could say that this is continuous on the closed interval from 2 to 2. We can say that because those endpoints, okay, we don't have any other graph after it. And so like the right-hand limit exists and it's the same as that point. And so since there's no more graph after it, this is just all that we have in the domain, we can say it's continuous across the entire domain. Does that make sense?
Okay. Since there is technically no thing that's not, that doesn't break the rules.
Right. Okay. Now here, these have to be open intervals because the limits are going to break our rules. But here, like since there's no more graph, like the domain is just -2 to 2, we can say it's continuous across the domain, -2 to 2.
Yeah.
But it doesn't, but at -2, there's no left.
Correct.
No curve from the left there.
Correct. But the right-hand limit is the same as that function value. And since there's no more domain left to look at, as long as that one side of the limit is the same, then it's okay. Since we're talking about an endpoint.
You're smart with me, but
Oh, thanks. Okay. All right. Now,
Did you see it? Sweet.
You missed it. Okay, so here I have a piecewise function. I want it to be continuous. What needs to happen for this to be continuous?
Those 2 points have to be at the same point. Same.
Okay.
The limit has to exist.
Okay,
Yes.
the limit needs to exist at 2, the function value needs to exist at 2, and,
Function value, no limit.
And that means.
okay. So, right now you guys are really worried about this limit, aren't you? Okay, so let's look at the limit. It's a piecewise function, so what are we gonna be worried about? Of 2. We need to worry about this break. Is it gonna break apart? We don't want it to break apart, we want it to overlap, right? So we need to look at the left and right hand limits of 2. So the left hand limit, we would need to use what? Ax squared. And what would that limit be? 4a. Okay. The limit as x approaches 2 from the right, we're going to use this piece, x plus a. And that would give us 2 plus a. What needs to be true about these 2 limits? They need to be the same. So 4a needs to equal 2 plus a. Which means a is
2/3. Can you subtract the a over and then subtract the a divided by
But
2?
then you end up getting a minus a.
Which is you get 4a minus a.
Well, you
4a
should
minus
divide
a
by
is 4. It's not, it's simple.
No, you don't divide by 4. You subtract the a and you get 3a.
Jeez.
okay. So, okay, now let's check. If I evaluate f of 2, because we need to have a value there, we would plug 2 into what?
3. For x. So it'd be 2/3 times 4.
If you could take it to a.
So it'd be 2/3 times,
4.
what?
4.
2. Thank you. So we would get 8/3. That's our function value, right? And if we look at our limits are going to be 8/3 as well, right?
Because 2 plus 2/3.
This is me checking my work. F of 2 is 8/3, right? Our limit would be 4 times 2/3 is 8/3, and 2 plus 2/3, which is 8/3.
Basically just force
I plugged A into my A's to make sure they were
There's
okay.
2/3. We found it there.
Okay.
I thought you plugged them into the original equation.
We found A. I did.
But then you plug them into your a too.
Well, we need 2 in for X and A in for in. We found it. We'll just stop there.
Okay.
Does that work?
Yeah.
Okay. I was checking my work, but now I'm losing people, so we are going to stop at A. Okay? Is everyone okay with A is 2/3?
Yes.
Our right and left hand limit equal, and we solve.
Oh wait, so we don't have to plug a.
Nope, we're not all about it.
I can't even do simple algebra.
Okay. 2 types of discontinuity. You need to know the difference. We have removable discontinuity, which means we have a way of rewriting it to remove it, such as a hole. We can fill that in with a point. We can remove that discontinuity. Okay? Non-removable discontinuities. We cannot rewrite our function to take that discontinuity away. Any ideas of what that might look like? An asymptote is a non-removable discontinuity. So let's look at what these look like. This is a removable discontinuity because we can either, okay, we can fill in that hole by making this a piecewise function. If I make this a piecewise function, when x doesn't equal 1, I make that 2. When x equals 1, I fill in that hole and it's now continuous. Right? Or we can say this is the line, what, x plus 1, okay? Or we can say this is the line y equals x plus 1, and that is continuous. We can remove that hole if we rewrite our equation. Okay? There is no way to remove this discontinuity. 1 over x is 1 over x. We can't take away that the asymptote. The asymptote is there to stay. Okay, an asymptote is non-removable. Yes?
Would another removable one be like when we had like x squared minus 1 on the bottom and we separated it and canceled and stuff?
Right, because that's when there's a hole. Right, when we have factors that cancel, that's a hole, and so we call that non-removable, or we call that removable. Right. Okay, so let's look at some. Okay, I want to know if our function is discontinuous anywhere, and if so, what kind of discontinuities do we have? So tangent of x. It's what? What? Where? So we are discontinuous. We have what? We have asymptotes at x equals pi over 2, x equals negative pi over 2, pi over 2, etc. Right? Okay, so these are pi apart, beginning at pi over 2. Now, if we wanted to write that, we could say we have asymptotes at pi over 2 plus pi n. So our asymptotes begin at pi over 2, and they're every pi apart. Okay? And what kind of discontinuities are these? They are non-removable. Okay? What about this? Yes. Because there are asymptotes there, we can't change our function to take those away. Because it's the tangent function, we know that there's asymptotes every time we change the line. Okay. 2x cubed minus x. What kind of function is that? It's a polynomial, which means it's continuous. Polynomials are always continuous. Every time. What should we probably do with this equation? Let's factor it to see if we can simplify. So we have 5x over okay, sorry. So we can cancel out our x's. So what is happening at x equals 0? A hole. So at x equals 0, we have a removable discontinuity. What?
Yeah,
Also, at x equals 1, we have a asymptote. So that is what kind of discontinuity? So that's non-removable discontinuity. I don't want to spell that word again.
We spelled it wrong first.
I know, that's why I scribbled. Okay. You try to talk and write at the same time. Okay.
So how do we, like, I'm getting, like, how do we know there's a hole in asymptote looking at the rational function?
Okay, if you have factors that cancel, we have a hole there. If your factor doesn't cancel, asymptote. Okay? Ooh, look at number 4.
Let's do the limits.
What did you say?
We have to do the limits.
We need to see if we have a break or not in our piecewise function. So we need to look at the limit as x approaches 0, from the left and from the right, because that is where our domain breaks. So what is the limit as x approaches 0 from the left? 4. What's the limit as x approaches 0 from the right? So what's true about this function? Okay.
It's continuous.
Thank you. It is continuous. Because we have 2 pieces of continuous functions that are overlapping at that domain break. So we're good. Who's the clap for?
Jimmy, just solve it.
So we did it. Okay. Now, let's talk about this.
Oh,
there's more.
there's more.
And there's more.
17.
Composition.
Well, it's just not, it's like good.
Come on, Zach.
That's no fun.
So what should we probably find? Okay, first of all, we need the composition. When we plug G into F, what do we get? So this is continuous?
Yeah, because nothing like could make it negative. Oh, it could be -4 or negative. No,
Negative something. What?
negative something that
Could make it so.
Multiply something.
I got talking. I was saying like.
Could multiply something by
Negative
Negative 7/3. What's happening at x equals negative 7/3? Is an asymptote. So what kind of discontinuity?
That's what I said.
Non-removable discontinuity. Here are some properties. You guys just look at this, okay? I would not suggest writing all of these down, okay? Let's just think through these.
That's what you want to do. That's what you want to do.
Okay? If we're continuous at a point on 2 separate functions, okay? Well, if we have a scalar multiple to our function, that's not going to change the continuity. If we add our 2 functions together, as long as they're continuous at that point, when you add them together, we're still continuous. Product. If f and g are continuous at a point, you multiply them together, they're still continuous at that point. Same thing with the quotient. You divide them, they're still going to be continuous at that point. Okay? These are things that we need to talk about, but you've kind of, I mean, they're kind of, I don't want to say common sense, but they make sense, right? I don't think we need to write them down because we can talk through them and, yeah, okay, that sounds good.
All right.
Okay? And then we looked at the composition just now, okay? If G is continuous and F is continuous at G of C, okay, so if G is continuous at C and F is continuous at G of C, why are they saying G of C instead of C? Okay? The outputs of G are the inputs for F, so we have to say G of C. So as long as it's continuous as you're composing, then your composition is going to be continuous.
Question.
Yes.
Say, can you go previous page? G, so say G of X was equal to, you still have H of X equals F of G of X, but G of X equals X plus 8 over X plus 7, and then F of X equals 3X. How would you do that? If you-
Okay, so if we were composing the other way?
Yeah.
So we'd still compose, but then, so we would have 3 of x plus 8 over x plus 7. So now our discontinuity would be at -7.
Okay.
Okay, excellent. Okay, your first AP question.
Everybody's got it.
So disorganized. Sorry.
Was this like on the AP test or something?
This is like an AP question, yeah, so I want you to read through it.
Oh, man.
If your answer is A, don't say anything. So A, B, C, D, E. Ready? Give me your answer.
Hold on, I'm still A, C, A, E. The 3 of them.
What is this?
That's not D and
I'm gonna
E.
do this. I'm gonna do this.
Okay,
Oh, I think it's like, pretty
It's
sure it's
Edo,
all
right?
there.
It's Edo.
Oh, 2 is not true. It's not gonna be.
so let's go through these. Does the limit exist?
Yes.
What is the limit as x approaches 3? Okay. Is f continuous?
Yes.
We just figured out.
Okay. So our limit is 6, and our function value is 6. So, yep, we are continuous. X equals 3 is a vertical asymptote.
No.
No, because it is a
Dot.
pole.
Hole.
So your answer should be,
D.
Wait, what?
I couldn't
What?
think of D
You
though.
just said one
It says does not exist.
oh, it says does not exist. See, that's where the AP test likes to trick us. I read it as does exist, didn't I? Yeah,
Oh, wait, so can you explain why it's continuous?
yes.
Yeah.
So if we look at the limit from the right and the left, we see that it is 6, right? Do you want me to go through that limit?
So,
And it equals 6.
Okay, so first of all, we'd say this is x plus 3 times x minus 3 over x minus 3. So those cancel. We have a hole at x minus 3. When we look at the limit from the right and the left, our limit is 6. So the limit exists. And our function value, so if I take f of 3, it's also 6. So since the limit is 6, our function value is 6, we are continuous.
So just the 6 right there, like 6 comma, that
Hold on.
shows that there's a, point, that means like f of c is 6.
So that this is f of x is 6 when x is 3.
So how do we know that the
So
limit
did you
does
just plug in
exist?
because it's 6.
Okay, so if we look at, so
The
this
hole
is,
there.
what?
If it does
But
exist,
there's like a dot on
So what is this graph? This is a graph of x plus 3 with a hole at 3. So the limit is existing, right?
then it wouldn't be continuous if there's a hole.
Right, but see, that's what this is doing. When x is 3, our function value is 6.
Oh,
It's filling that in.
In like the top, if you plug 3 in for the x at the top.
Right, that's how we would evaluate our limit, right? Yeah.
Oh, alright.
Yeah. Okay. We good?
Get through this.
Does that make sense?
Excellent.
Let's not let it.
Okay. So, what I want you to do is you have some homework problems, but I also want you to think about what we're gonna, part of what we're gonna talk about tomorrow. So a part of continuity is the intermediate value theorem, okay? And instead of me saying, this is what the intermediate value theorem is, I have a couple things I want you to think about, so you can kind of understand where the intermediate value theorem comes from. So this is going to lead us in a discussion for tomorrow's notes. So I need you to have this completed so you can participate in our discussion for tomorrow's notes. And then tomorrow we'll go over this and infinite limits and have a homework assignment. You can keep this.
You said the little video was online, so you want me to like see this online?
Okay, so what I want you to do is I want you to fill it out. I want you to do
I
it.
already know what the intermediate value here is.
Okay, then fill it out, go through it before you watch the video. The video will not be posted until tomorrow afternoon, okay? Because I'll record myself doing the notes tomorrow, okay?
Why do you have to target that?
For people.
Oh, they know if you were.
For what? We should have room in our house.
Okay, so John, we wanted to go through this problem, right?
Yeah.
Okay. Is that everything? Oh, I'm so recording.
Good.